Welcome friends. In this video, we are going to cover regression analysis, which is basically an extension of correlation analysis. So those who have not seen the correlation analysis video and not clear with the correlation aspects, they are advised to first see that video and then come to this. Now this regression analysis is in multiple parts. So we are going to cover the first part, that's the basics of regression analysis using SPSS. So friends, here in the correlation part, we saw that the correlation between performance and salary can be visualized through scatter plot. Now in scatter plot, there are two aspects of that. One is the slope of the line, and second, the nearness of the point to the line. So if the points are very much near to the line, the correlations will be very high. If they are all on the line, we say perfect correlation, right? But the second part, the slope of the line, that also indicates something. Okay, so we want to see if logically we know that performance score does impact the salary, then we would like to know, or we'd like to frame an equation to predict the salary or to understand the salary, how much impact the performance score has on the salary. So logically we know the performance does influence the salary, and this we want to evaluate through regression analysis. Okay, in earlier part we can do with a correlation, whether just they are correlated or not. And that's only correlation coefficient. Here we are going to evaluate using regression analysis. We are going to quantify the impact. Okay. So the hypothesis or research question is, does the performance has any relationship with salary? And we say yes, it is there. And now we want to quantify that. So for that, we are going to use a regression analysis. And also in this part, we want to understand the meaning of R square. The first meaning is that R is the square of R. That is square of correlation coefficient, right? But in regression analysis also, there is a R square value which is coming. If it's a simple regression between one independent variable and one dependent variable, it's exactly the same as square of the correlation coefficient. But if it's a multiple regression, the meaning changes. So let's try to understand that meaning first. So I'm going back to the ice cream example. And we know that in summer, the temperature is high. And because of that, the sale of the ice cream is also high. So I'm going to put the temperature of the heat as a variable which influences the sales of the ice cream. Okay, the heat we are going to denote as X, independent variable, and the sale of ice cream we are going to denote as a Y, that's a dependent variable. Now, let's say I have a data for 4 different time. So I found that when the temperature is 17 degrees centigrade, the ice cream sales was 341, and so on and so forth. And when we put a scatter plot, we see there seems to be a positive correlation. Okay, between sales of an ice cream and the temperature of the day. Let's say in general, if we don't know anything about the temperature of the day, and let's say somebody comes to you and say, okay, I have 4 data points of the ice cream sales. Can you predict the ice cream sales for future, or let's say in general? So normally what we do, we say we go by the average, right? So if you find the average of this 4 data points, let's say I have removed the decimal point, roughly 300, just for the sake of simple analysis. So if you go by the average method, our prediction was, let's say our expectation is, or prediction is 300 kilogram of ice cream will be sold. But let's say if you compare to the past data, we find that 341 was actually sold. It was oversold, right? Here it was less than the prediction, here less than. So there's a difference. Let's quantify this difference. So we are going to use Y minus Y average. That is this value minus average prediction, square of that. And these are the difference. These values are again rounded off based on round off values. And the total sum of the square of the error is 2811. Total sum of the square of the error. Error is what? 341 was actual. We predicted 300 based on average. So error is 41, square of that, and so on and so forth. Now, you know that the sales of the ice cream is influenced by the temperature of the day. So you collect the data for the temperature of the day. Now we have this data. Let's say we made a scatter plot, and by some means, we'll see later on how to find out that. By some means, you frame an equation. That is Y is equal to, it's mx plus c, right? Straight line equation. Here it is denoted something like this. Y is equal to, it's the same equation, just the notations are different. The Y is equal to beta naught, that's a constant, mx plus c, that's a c part, beta naught plus beta 1 times x. So beta naught is the constant or intercept, and beta 1 is the coefficient for x. Okay, so we can frame this equation. Now, we'll see how to frame this equation, how to get the beta naught and beta 1 value. Let's say by using this equation, can we predict the sales of ice cream using the temperature? Yes. Plug in this 17 value into the x, and you get the y. So let's make a prediction. Okay, you can take a pause here and do the calculation. Now, once you predicted, now let's compare this prediction with the actual values. You find that actual value is 341. We predicted 333. The gap has reduced. Earlier the gap was 41. Now the gap has reduced, right? Similarly here. So let's find out the sum of the square of the error in the new scenario. Same formula. Actual minus prediction, square of that, and sum of that. So now we find that the sum of the square of the error between actual and the prediction has came down to 324. If you go by the average method, it's a 2811. If you go by the equation method, it's a 324. So the sum of the square of the error between prediction and actual has reduced if you go by the regression equation. How much we have reduced? Let's do the simple calculation. 2811 minus 324, this is reduction, divide by 2811 in terms of percentage. So we get 0.88 or 88%. Now this is called R square value. So using the regression equation, by what percentage you can reduce the sum of the square of the error between the actual value and the predicted value. Okay, also called coefficient of determination. So the meaning of the R square is that this is the amount by which the sum of the square of the error can be reduced if you use the regression equation instead of going by the average method. I hope this is now clear to all of you. So when we say here R square 0.146, the meaning is that if we frame an equation to predict the salary based on the performance score, that equation will help you to reduce the sum of the square of the error to the tune of 14.6%. It's not very high, but it will help you to reduce. Now, somebody who is in HR or who is in personal department, they know that the salary is not only the function of performance score, it is something more parameter as well. So if you include more parameter, the equation will become more elaborate. And accordingly, the R square value will also improve, can improve. Now, let's do this regression now. We are saying the performance score does not influence the salary, and the performance score does influence the salary. So let's see this hypothesis we are trying to test, and I will try to bring it where the equal to sign comes in here. Okay, later on, not now. So please go to the analyze, regression, and linear. This window will open. Now in this window, unlike correlation where we put both the variables together in the same field, in the same box, here we have to be very, very careful. The salary is my dependent variable, which we are trying to predict. Okay. And based on what? Based on performance score. So performance score is my independent variable. When we say independent, doesn't mean it is not getting impacted by anything in the world. In this relationship between performance score and salary, the performance score is the independent variable which influences salary. And hence the salary is a dependent variable. That's the demarcation you have to put. So bring in this point, these variables here. And then click OK. Once you click OK, you will get this output. So let's see the output here. So output is a 3 window. We'll start first with this one. This says that if the F test, if F significant is less than 0.05, we are going to reject the null hypothesis. And what is the null hypothesis here? The null hypothesis is that the prediction using the average. Remember ice cream sales example? The prediction using average values is equal to prediction using equation value. Now, friends, if the null hypothesis is rejected, what it means? That the prediction using equation are significantly different from the prediction using average. If the null hypothesis is not rejected, that means if the F significance values is not less than 0.05, it is more than 0.05. So we say at 5, percent level of significance, I'm explaining if the significance value was more than 0.05, then in that case, we will not reject the null hypothesis. So what is meaning of that? The meaning is that the prediction value using equation is more or less same like prediction using average. If that's the case, then don't use the equation. Just go by the average method, right? In our case here, the significance value is less than 0.05. That means this hypothesis is rejected. That means the prediction using equation is not equal to average. So don't go by the average. Go and frame the equation and use the equation to make a prediction. So my next point is that, okay, if I make an equation and make a prediction, how, by what percentage I will be able to reduce the sum of the square of the error? In this case, it's a 14.6%. It's a very low number. So here, F significant has to be less than 0.05. This value, higher the better. That's what the normal we do. Okay. So first step is this. Second step is this. Third step. Now we want to frame an equation. To frame an equation, what we need? We need the parameters for beta naught and beta 1. So beta naught parameter is given here, 25985. That's a constant. For beta 1, we have to first check whether beta 1 is significant or not. So here the regression outputs is doing one more hypothesis test. He's checking. He's conducted a t-test. In the t-test, the null hypothesis is that the beta 1, the coefficient for x equal to 0. Is equal to 0. So since the t significance value is less than 0.05, we reject the null hypothesis. We say, okay, the beta 1 is not equal to 0. And once this null hypothesis is rejected, the beta 1 is not equal to 0, then only we'll go ahead and pick up the beta 1 value from this. So pick up the beta 1 value from this and frame an equation. The equation has this particular format. Beta naught plus beta 1 times performance over x. Beta naught value is coming from, sorry, the beta 1 value, so beta naught value is coming from here. Okay, let me clear up all these things. So beta, these two values are going to this equation, the 25985 as a constant and 206.26 from the unstandardized coefficient value. Okay, now this equation we can compute the performance of a person. Okay, now what's the use of standard error of estimate? Remember, this is 14.6% only effective. That means there's a lot of spread in the scatter plot. That means there can be error. How much will be the error? And to accommodate that error, we have to predict and then give a range. And to give a range, we are going to use standard error of estimate. So let's say if you want to compute the 95% confidence interval for the prediction, then the Z value for 95% level of confidence is 1.96. And the standard error of estimate, which is coming up from here, 6758.8. That we are going to use. So now let's say if you have to predict the salary for a person whose performance score is 80, then we will plug in the 80 value here, plug in this value here, compute the prediction. Let's say it came out to 42,485, and then give a range using standard error of estimate. So in this case, it comes out to be, let's say salary will be around 29,000 to around 55,700. That's a range for the person whose performance score is 80. I know this is a very big range, and we know that the salary is not only dependent on performance. So later on, if you add more parameter, I'm sure the standard error will come down a little bit or more. Okay. Okay, now we are trying to check the hypothesis whether stay influences salary or not. Same method. Earlier we checked the performance, and we got output. So let's quickly do it now. First, we'll check this. The null hypothesis that the average prediction equal to equation prediction is rejected. We'll go and frame the equation. The equation will be effective to the tune of 39.5% reduction in sum of square of error. And the equation what we are going to frame, the beta 1 coefficient is significant because the t significance value is less than 0.05. So using these two values, we are going to frame an equation. And using the standard error of estimate, we are going to put up a limit. Okay. So friends, that was on the simple linear regression, where only one independent variable or one predictor is there. In the first case, it was performance. In second case, it was stay. But we know the salary is dependent on multiple parameters. So we can expand our equation and say, okay, beta 1 times x1, beta 1, beta 2 times x2, beta 3 times x3, beta 4 times x4. And now to do this in spaces, the same method, analyze regression linear. What we are saying, 4 parameter, age, performance score, stay, and TC, technical competency, influencing salary. And for that, we want to frame an equation. So analyze regression linear, put the salary as a dependent variable. Now the independent variables are 4. Do this, get the output. Okay. The method to interpret the output is same. First, check the F significance, which says the prediction using average equal to prediction using equation. This hypothesis is a null hypothesis. Since the F significance is less than 0.05, we reject the null hypothesis and we say it is not equal. It is different. So hence we can frame an equation. If you frame an equation to predict the salary using these parameters, how much is going to be effective? We say, okay, the R-square value is 0.535. Now here R-square is 0.535. It is not the square of the correlation between two variables. It is the square of the correlation between predicted value and the actual value. So let's say if you frame an equation, then you can compute the predicted value for all the given data. And you have actual salary also. If you correlate between these two values, the correlation will come 0.731. And the square of that is 0.535. And when say 0.535, that means the regression equation is going to be effective to the tune of 53.5% to reduce the sum of the square of the error. And what's going to be the equation? The equation will have here only those parameters we are going to, so our standard equation having 5 parameters, constant plus 4 coefficient for the 4 variables. Now, does all variable are going to remain in the equation? To check that, we have to check the null hypothesis for individual coefficient. For age, does the beta coefficient for the age is significant? Yes. Please take up that. Does the beta coefficient for performance score is significant? Yes. So please pick up that. Does the beta coefficient for stay years is significant? Yes. So please pick up that in the equation. Does the beta coefficient for TC is significant? Yes, it is significant. So please pick up that. And using this, frame an equation. If for any of the variable, the T significance value is not less than 0.05, do not include those coefficients into the equation. And you have to drop that variable altogether from the equation. In our case, all the 4 variables will be included. So my regression equation will be a longer one. Again, using the standard error of estimates, we can compute the limit. Now, if I give you the age of a particular employee, his or her performance score, his stay with the company, and his technical competency, you can predict the salary, right? Now, since there's multiple regressions, we have few more interpretations. First of all, the age is impacting negatively. When the age goes up, the salary goes down. The performance scores impacts the positively. Stay years impacts the positively, and TC impacts the negatively. Among these 4 parameters, the performance, the stay years has a highest influence, and that we are going to interpret using the standardized beta coefficient. Please do not use this value to compute the relative importance because they are of a different scale. The age is in years, performance score is in percentage, stay years in years, TC is in some other competencies between 1 to 7. So use these values. This is a standardized value. That means in all the 4 variables, the values have been standardized with the average equal to 0 and standard deviation equal to 1. And if you do the regression with those values, then these are going to be coefficient. So now it's apple-to-apple comparison. And in that, we find that the stay here has the highest amount of beta value. You have to ignore the sign. The highest amount of value is 0.634. So we can say the stay here has the highest impact onto the salary. And that can be verified through the scatter plot between stay years and salary. See, the scatter plot is very much dense around the line. And compare the scatter plot of age and TC with the salary. So it's very much spread out. Hence, those values are lower. Okay. That's all on the regression. So what we saw, we checked that we understood the meaning of R square, that is by what percentage the regression equation will help you to reduce the sum of the square of the error. Then we conducted a simple linear regression with only one independent variable for a dependent variable. We understood how to interpret the values. First, F significance has to be less than 0.05. Then R square value higher the better. And using the T significance less than 0.05 as a criteria, compute the equation. And pick up the value for beta naught and beta 1. Use standard error of estimates to compute the limits. Same concept can be applied for the multiple regression, where there are multiple independent variables are there. Thank you very much, friends.